Hi everyone and welcome to this new video. In this video we continue the kernel development series and in this fourth episode of the series we will implement our own printf function. Because as things stand in the current implementation, so in the previous episodes we introduced the SBI call function that acts as the main OpenSBI abstraction through the eCall, right, the eCall instruction. Now, in this case, we just have a put char function. So we are only able to print single characters. And this means that if we want, for example, in here, look at this. We want to print the string hello world, we have to go character by character and we have to do put char of each character. And now we want to change that because we want to introduce a better abstraction. Specifically, we want to introduce the printf abstraction with the format strings and the variadic arguments. And so that's the objective for this episode. So let's get started with this. So let's talk about format strings. Now, if you are familiar with C, of course, you will know for sure the printf function, which is used to print strings to the terminal, to the standard output of the process. And these strings can be like simple strings like this one, like hello world, and they can also be format strings in which we have parts that change dynamically depending on data. So for example, the answer is, and then there is this %d. Now these things, when it gets printed, it actually takes the value from the variable answer, which is 42. And so it's going to print out the answer is 42. So that's the idea. Now, if we check out the main page, we have different versions of printf functions. And in this video, we are mainly interested in the printf, in the original printf, in the simplest of them all. Now, these functions, as you can see here, they have this dot dot at the end, right? They have this dot dot at the end, or they have this va underscore list. Now, these functions are called variadic functions because they can take an arbitrary amount of arguments, right? I mean, just look at the example before. The example before, the first time we only have one argument for the printf. For the second call, we actually have two arguments. And we can have a printf with 3, 4, 5, 10 arguments. We can have a printf with an arbitrary amount of arguments. We are only limited by the stack of the process. So that's the idea. Now, in general, variadic functions basically can take an arbitrary number of arguments, and the printf is a classical example of this. So here we have even more examples. Now, when you want to program a function that takes an arbitrary amount of arguments, you want to use these kind of abstractions. So in this case, for example, here we have a simple C program with a variadic function that takes an integer n and then a variadic number of arguments, and we use this abstraction. So we use the va list arguments, we do the va start and va end. Okay. Now va start takes the last argument here n before the before the start of the variadic part of the arguments. And basically, we can do va arg to extract the arguments, and we can cast it to a given type. So for example, in this case, it's a char pointer, so it is a string, basically. And so in this case, if we execute this, we would get first, second, third, right? And I mean, you can take this code, by the way. You can call it variadic.c. You can compile it, variadic like this. You can execute it, and you get the following things, right? Actually, here, let's not put new line. Let's put just like a dot. So let's execute it like follows. And basically, this is what we get, right? So here I'm going to put new line here and there to make it more pretty. Now notice that the first argument is the amount of arguments that we have, right? Now it is important to understand that this va start, like if we do main va start here, we have variable argument list, and here we have va list ap last. right? So this last, where is it? The argument last is the name of the last argument before the variable argument list. That is the last argument of which the calling function knows the type. So in this example, there's something that might confuse. This is not the size of the number of arguments that we put, right? It's just the last argument. You know, if here I had an int a, that would be a, right? Now, why do we need the size? We need the size in one way or another because we need to know how many times we need to call the va_arg function, right? For example, when we call printf, we actually infer the amount of arguments by using the percentages like %s, %d, etc. So those kind of things implicitly define the number of subsequent arguments, because otherwise we don't know how many times we have to call va_arg to extract the next argument from the variadic list, right? So that's the idea. And so this is a simple example. Here you put 1, 2, 3. So it's a simple way to just show how to work with this approach, right? Now, in RISC-V, of course, what is the idea? Well, the idea is that when you use this kind of variadic functions, some of the arguments are passed through registers. Like, for example, the first 8 integer pointer arguments are passed in registers A0 through A7, while the first 8 floating point arguments are passed in register F80, F87, and the rest of the arguments are passed through the stack, because at some point you will finish the amount of general purpose registers, and so the extra memory, the extra arguments you pass through the stack memory, right? And by the way, I've made video in the past related to Linux calling conventions, in which we also analyze the stack trace. So if you're interested in that, check out the binary exploitation video on Linux. And so basically that is the idea, and now we can actually start to implement our function. Now this function is actually found, we will implement it into a common header, into a common, into a new file, not into kernel.c. Why? Because we want this function to also be exposed to the user space of the system, since it is a common function that is often used both in kernel space and user space. This means that we will create two new files, common.h and common.c. Now in common.h, of course, we have the typical guard, if and def common.h, we define common.h, and then we do and if, and here we comment with common.h, so that's the first step. Now here, we're actually going to define a voa list, voa start, voa end, and voa arg. So start, end, and arg. Remember the variadic example. Here we have start, end, arg, and list. Now, in the example that I've showed before, variadic.c, we had included this header standard arg, which expose the voa list type, the voa start, end, and arg macros, right? So that was the idea. This time, we cannot use such library because we do not link with the standard C library. Therefore, we will have to use the built-ins of the compiler. So the compiler offers the built-in voa list, the built-in voa start, and the built-in voa end and arg. So basically, we're just gonna go with the built-ins here. So we have list, start, end, and arg. Perfect. And last things, we just need to declare the printf. Now this printf is going to take a format string and then a variadic number of arguments. So that is the idea. So here we have this defines, here we have our printf, and then we're good. Now at this point, we can actually go and implement it into the file common.c. Okay, so here we include the common.h, perfect. And we bring the implementation for the printf. Now here we have the void printf const char fmt and then variadic arguments, perfect. Here we define the voa list args, the voa start with args and fmt because it is the last known argument, the last argument of which we know the type, const char pointer. And here at this point, we have to implement this function. Now, this function will actually internally called the put char, right? And the put char here, we don't have the implementation for the put char because this is found in kernel.c, right? Here it is where we define it. So what we can do here is you can just declare it like this so that we're going to be able to use it when we get linked with the kernel.c. Right, so at this point, we have to modify the makefile because now in the source, we have to add a dependency which is common.c. And now, if I do make and make run, if I do, okay, here I have to go into content, of course. I can remove variadic and variadic.c, whatever. I do make run, and here I get my normal execution because, of course, nothing happened there. But at this point, we actually get access to the common.c. So the common.c is included in the compilation process during compilation. So at this point, we can actually implement the logic for this printf. So what is the idea? Well, we start with the way start, and here we end with the way end of args, basically. And here we have to read the various characters of the format string, and we have to print the according character into the output, right? So we say while fmt is not equal to the null character to the end of the string. So basically this means until there is something that as long as there is something to read, right? Until we are completely done, what we do is, okay, this one is different from the null character, so there is something to read, and so we have to read this value. So at this point we say, look, if fmt is not equal to this percentage, then we are just going to treat that character literally. We're just going to print it as it is without any complication. So I'm going to do a simple put char of fmt, of the not fmt itself, because fmt is a pointer of the character that is pointed by fmt. So fmt points to a bunch of memory, right? These bytes of memory. At this point, we get the value with this syntax. We are reading the value itself of the byte here, right? 0x, 4a, whatever. Now, if this is different than null, we say if this is different than percentage, then we just need to print it exactly as it is. So that's the idea. Now, otherwise, what do? We have consume a percentage, so we can do fmt plus plus. Then we're gonna switch once again on the fmt. So actually, before we do not even switch on the fmt, here we switch the first time. And why do we switch the first time? Because after the percentage, we could have many different options, right? For example, we could have percentage %s, we could have percentage %d, we could have percentage %x or percentage %p, maybe. And sometimes we can also have percentage, which in classical printf implementation, this is just a single literal percentage character. It is a way to escape it, basically. So that's the idea. Now, what happens? Well, if we reach the end of the string, so at this point, if we have reached the end of the string, we just put char that percentage, because in this case, that percentage was actually a literal percentage, and we do a go to end. Now, go-tos typically, like when you use go-tos at university, they typically say they are not good. However, they can be good as a cleanup, as a defer mechanism, in a way that we are just jumping to the end of the function, basically. And in this end of the function, we have the VUA end. So we skip all the logic that goes from this point to the end. This is sort of like a defer to execute a VUA end in a deferred way so that it is executed every time we are done with that specific computation. And so that's a specific way in which we can do this. Now, another case that we need to handle, of course, is the percentage itself. Another case that we need to handle, so here let me just put it like this, and then we're going to do, okay. Another case that we need to handle is the percentage %s, okay, when we want to print a string. And another case that we need to handle is the percentage %d for the integers. And finally, we have the last thing is we have the percentage x, which is the hexadecimal, character. Now, at the end here, before, for the next iteration of the while loop here, we actually have to increment fmt once again. Why? So remember, in this case, we are consuming this percentage, and then we are switching over the next character. So basically what happens is that if we go into the first if, we just put the character, and then we have to increment it. Otherwise, we're actually going to increment it 2 times. It's just that the first one is to consume the percentage, and then the second one is to consume either the null character, but then we go to the end, so we are done, or these other 4 cases. So in these other 4 cases, at the end of the day, we just consume 1 character. And so basically, we can just put a fmt++ at the end. So at this point, what we need is just to handle the logic for each specific like format string modifier. Like for example, this one. Now this one is pretty simple actually, because this one is just a literal put char like this, and then break. Like in this case, we don't go to the end, we don't do go to end, we just put the char and then we break and we go to the next iteration, right? And so this is literal percentage. So this is string, this is integer, and this is integer with sign, and this is hexadecimal, the hexadecimal representation. For example, 4 pointers and things of the sort. Now, the literal case has been handled because it's pretty simple. Now at this point we need to handle the string case. Now the string case, what do we do with the string case? Well, with the string case here, basically, we need to extract from the argument a string. So we're gonna say const char value equal vararg args, and then we cast it to the type const char pointer, right? And so at this point we have a for loop in which we check until the value is different than the null character. We're gonna increment the value, of course, and we're gonna say put char of value like this. And then we're gonna break as that we already have. We can also put it like in a single line like this. So basically we are doing, printing each character one at a time. And we are getting the argument from the list of the variadic argument. So this is one of the easiest case because we don't need to do any conversion. We can just use the already existing put char. Oh, and by the way, in this case, here we can already test it partially, because if we don't use d or x, we should be good. So let's try to test it. Let's to make, so it says case label not within a switch statement. So what's going on here? Switch, okay, here, of course, I did it wrong, basically. So here, let's just put curly braces in here, and let's put curly braces in there. Okay. So because it got confused for the closing curly brace, I do make 42 common.c. So common.c 42 is like in here, basically. So this while, so this one is for the switch, okay. Then I have to close the else statement. I have to close the else statement. I have to do the fmt. So I have to do the fmt to go to the next character. And this has to be regardless if you go into the if or into the else, basically. I guess another way to put it could be that we say like, okay, I put char and then I increase, otherwise I put char 1, and then here I'm gonna do at the end, I'm gonna increase it once again. So this is another way to, maybe it's more clear like this, I'm not sure, you tell me, that we have clearly the situation in which we are like incrementing. So else we are consuming this, and we are consuming here the modifier, consume modifier, percentage modifier, like this. So let's make, now we can make it run. Now, of course, it's gonna work, but what we want to do is we want to test it out with a simple printf, and then here just like a string like this, with s in here, basically. So something like this. And of course, here we need to include common.age. So let's see, make run. Now notice that it works. It prints out the string. So now we are already using this abstraction. However, we have not completed it because right now it only prints the strings. But the actual most interesting things happens when we try to print the integer and the hexadecimal value. And so right now we have to print the integer and the hexadecimal. Now let's think about how to handle the integer, because with the integer it is less trivial to understand how to print it. So this time we don't have a const char pointer, but instead we have an integer. So we say int value, we're going to say void underscore args, void args, and then here int. So we get an integer. This can be a positive number and it can also be a negative number, okay? So what is the main idea behind how we're gonna print it? So basically, when we have the number itself, we have to find a way to extract the digits out of this number. And to do that, we will use multiplication, division, and the modulus operator. So what's the idea? Well, first we're gonna try a simple like a simple approach that works with positive integers. So the first thing that we will do is we're gonna divide our number by increasing powers of 10 until we reach 1, where the division of our number with the power is less than 10, basically. So we say unsigned int power equal 1. We say while value divided by power is greater than 9. So while it is at least 10 or greater, what do? We do power times 10. Like we just increment power by 10. So what is the idea here? Let's say that our input is 4321. Okay, now with this algorithm, what we're computing is we go in the loop, we start with power 1. Now, value divided by power 1 is clearly greater than 9. And so basically in this loop, for this case, power is going to become 1000. The next iteration, it becomes 10,000. Now 10,000 divided by, this divided by 10,000 is less than 9, and therefore we have a problem. So we have a problem and we stop there, basically. So that's the idea. Now, after we have this power, we're going to extract single digits from our number. How? We say while power is greater than 0, what we're going to do is we're going to extract value divided by power, and we're going to do put char of 0 plus value divided by power. So this is the digit that we're printing as ASCII character. And then we have to update the value. Here we do the modulus with the power, and we have to decrement the power by a power of 10. So we are decreasing the power by 10. So what is the idea here? Well, the idea here is that if we have 4321, power initially is 1000. Now, when we do value divided by power, we're going to get 4. We're going to get 4 because in C, when we do this kind of division, we do an integer division, which means that we don't have decimal points, right? We just have 4. Then we are updating the value with the remainder with the division by power. So the division by power has a quotient 4 and a remainder of 321. So at the second time, we're going to have 321. And power, we are dividing by 10, so we're going to get 100. So we print 4, and then we have these two other numbers. In the next iteration, we're going to print 3, and then we're going to have 21 with 10. We're going to print 2, then we're going to have 1 with 1, we're gonna print 1, and then we're gonna like basically have a 0. And we're gonna stop at some point because this is an integer type, and therefore when we have 0 dot something, that will be transformed, truncated into 0 itself, right? And so that's the idea. However, this is not the whole truth. This works but with positive integers. It does not work with negative values, right? So for example, let's just extract this piece of code. Let's put it into example.c in here. So basically we would have int main void, we have this, And here I'm gonna say value 431 include stdio.h, right? So here we're gonna say puchar like this. So let me compile this example.com. Example. Now notice that this time it works. Now what happens if you do minus this thing, right? Minus this thing, it does not work anymore. Why is that the case? Well, that's the case because when we have minus integer, the underlying bit representation is different because we are using choose complement. So to handle negative values, we need to change it up. So how do we do it? Well, first of all, we don't do operation with the sign. So we want to remove the sign. And so basically we want to transform the value into a magnitude like this. And then every time here we have value, we want to transform that into a magnitude, right? Like this. Perfect. So that's the first step. However, even right now, if you do like this, it's still not gonna work, right? It's not gonna work. Why? Because at this point we have to say if the value is negative, right? Well, first of all, we have to put char the minus, and then we actually have to flip the sign of this thing. So we have to flip the sign of this thing, and we have to do, we have to sort of like extract the representation, the bit representation of the entire number. And the way we do it is actually like this. So we actually have to negate with minus like this. And now notice that it does work, okay? And why does it work? Because the idea is this. When we have minus, we are using choose complement, right? Now go and look a video about choose complement to get an idea. But basically, the bit representation is different. It is not the bit representation of the value 4321. Now, to get to the bit representation of 4321, we do this minus operation. With this minus operation, we get back to the bit representation of this positive value, and then we can just print it like we always do. So we have this little fix on top that handles negative values. So we can put that into the kernel, into the command, sorry, here, basically. And so the final code is this one, where we have the value that we obtain from the arguments. Then we have this thing with the magnitude and then this thing with the power. And so basically that's the way we go. And here I can just put some comments basically to explain the situation because of the bit representation that we're working with. This is what we do here, and this is what we do here with the printing of each digit. And so with this, we are almost done. Let's go into kernel. Let's try to print out some numbers now. So let's do %d, and here I do 42, whatever. I do make run, make run. Now notice that here we actually get minus 42. Now there is some space here that is, okay, here is this space. It's not minus 42. There is this dash, which is not really a minus. Let's do just a hello world without the new lines here. Now we do comma 42, comma 42, make run. And then here we have hello world, comma 42. So that's good. Now to finish off, let's consider how we handle hexadecimal numbers. So let's say we have an hexadecimal number, right? Like F, A, B, C, 1, 2, and then 5F, whatever. So this is an hexadecimal number that we can store in a 32-bit locations. And we're developing a kernel for a 32-bit system, so that's good. Now, every two of these letters, we are talking about 8 bits, right? Which means that every one of these letters is 4 bits, right? So we have 4 bits here, 4 bits here, and so on and so forth. So in total, we have 32 bits. So the idea is that we're gonna want to extract 4 bits at a time from this sequence and print those, right? So how do we do that? Well, first of all, we read the value as an unsigned integer. So unsigned integer like this. Then we're gonna iterate from 7 until I is greater or equal to 0, I plus plus. And then what we're gonna do is we're gonna extract the so-called nibble. So the nibble is a sequence of 4 bits. Now, how do we compute this? Well, let's consider what we would do for the first group, right? For the leftmost nibble, so to speak. So what we would do for that nibble is Well, we have to shift the number to the right. We have to shift the number to the right. How much? Well, we know that each group is 4 bits, and we have to shift it 7 times. Basically, by doing this, we are taking the 4 bits that are leftmost, and we are pushing them to be the rightmost one. So from the 4-bit leftmost, we are putting them to be the rightmost one. Now, after we do this, however, we have also to bit mask it with 0xf, because we are only interested in the last, in the first 4-bit of this new number, basically. So that's what we would do for the first nibble, right? For the second one, it's gonna be the same. It's just that instead of doing 4 times 7, we have to do 4 times 6, because now we're not interested in the like leftmost 4-bit, but in the second other group, right? In this other group. So we have to shift it, but 1 less here. And basically we have to repeat it until when? We have to repeat it until we are at 4 times 0, basically. 4 times 0. And so this is why we have this code. Here we have the for loop, here we have the nibble, and here we have this situation in which it is 4 times I. It's 4 times I, and then we have the bit mask with this other thing. So let me check the parentheses because maybe they don't match up. I think this is fine, like this, basically. It is fine like this, so that they don't match up, and then it's like this. Perfect. Now, once we have the nibble, this is going to be a simple number between 0 and 15, and we can use it as follow. We can put into a string 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, A, B, C, D, E, F, and in here we index this string with our nibble. And like this, boom, we have our hexadecimal. Let's just try it to make sure. So let's do string, and then we do string with s. Then we do, let's say, int a equals 42, int b equal minus 42, and unsigned int c equals 0x, and we say f1 a1 b1 b1 c3 d4, like this. So we have string, we have integer d with a, positive integer, negative integer b, and then we have hexadecimal with x, with c. So we compile that. So it's iteration invokes undefined behavior not within this loop greater than 0. Of course, here it's bad, I made a mistake. Thank you, compiler, because it's actually I minus minus. I minus minus, the compiler saved me in this. I thank very much the compiler. So what do you have here? We have hello world, we have 42, we have minus 42, and we have A1, B2, C3, D4. Of course, it's lowercase because in the common here we have defined them as lowercase. We can also do in uppercase, so it is fine. And so basically we have our printf abstraction, which is useful. Of course, we can even improve it in the future, but for now it does its job, and we can start to print out data in the kernel. And so with this, this episode is finished. Now, before going to the next episode, I want to thank you for having watched so far. If you want to support my work, you can subscribe to the Patreon. I also have courses on Udemy where I teach how to test out the security of a web application and how to test out the security of a Linux system. And finally, this series is based on the book by Seiya Nuta, Operating System in 1000 Lines, which is a great book that you should read if you want to learn how to develop a small kernel. So thank you very much, and to the next video.